Good evening all. Welcome to week 7 of this lectures for optimization from fundamentals course. To those of you who joined for the first time, so I'm Durga Prasad. So I'll be the TA for this particular course. Over the next another 5 more weeks, we'll have these particular sessions. These sessions help you to solve your assignment problems, and if you have any discussions, we can have. If you have any doubts or anything, we can discuss them during these live sessions. So I would encourage you to ask any questions that you have from the lecture videos of this particular week or any of the prior weeks. We'll wait for say a couple of more minutes to let few more students to join, and then we'll get started. Yeah, I think we should get started. So this week's topics are on forecast lemma, and then we'll see what is max flow or min cut problem. Both are, and we also see how both are equivalent. And then we'll see the alternate form of forecast lemma, and finally we'll end with what the complementary slackness condition is. Hi, good evening. Okay, we'll get started. Yeah. So the first concept is the forecast lemma. So here we have a matrix A of this dimension n cross m and another vector C of dimension Rn. And there are two statements here. This particular lemma states that only one of them is actually true. So the first statement is if you have a certain matrix A, which means this is certainly a certain set of equations. So Ax less than or equal to 0 will essentially mean you have a polyhedron. So if you recollect, we have Ax less than or equal to 0 will represent a half space, and when you take a bunch of them together, x less than or equal to all of them together will represent, like, if this particular value is b, then that particular it's essentially a polyhedron, but instead of that we are saying it is equal to 0. So this is one particular region that you have, and then C transpose x is less than 0. And the other statement says that A transpose y, there will, if an x exists such that these two conditions are satisfied, then no y will exist that can satisfy both these equations, and vice versa. So only one of them is actually true. The proof is actually quite straightforward. So if you try this statement, write this statement in this way. So this C transpose x can be taken as the objective function. So what we are trying to do is minimize C transpose x such that Ax less than or equal to 0. If you consider this as the primal problem, you can convert this as since this is a minimization problem, you can also convert into a maximization problem just by multiplying with a minus sign. So this will also be the primal problem. But if I convert from primal to dual, the conditions, if you recollect, if it is a maximization, it should be converted into minimization. Inequalities will be converted into equalities. So this maximization becomes the minimization problem. And the constraints become variables, and variables become the constraints. So here the constraint is this value is 0. So this goes into the objective function, that is 0. And then this A remains the same. And the C that is in the objective function will come here. So A transpose y equal to minus C, y greater than equal to 0. This is the dual form. Or if you see it in other ways, if you think this as a primal problem, consider this as a primal problem, and then you convert it into dual problem. This will be the corresponding dual problem. So it's like if you take the dual of a primal and then take another dual of it, and you will eventually get back the original one. So this is my original one. You convert it into dual, it's a p prime, and again you convert it into dual, then you will get back the p. if you see the equivalence of the statements from strong duality that we discussed last time, if a particular solution exists for this dual, then primal will also exist. But if primal solution does not exist, then dual will not exist, and vice versa. So what the first, if the first statement is true, which means if C transpose X is less than 0, or C transpose X is less than 0, so this will be some positive quantity, then Ax is less than or equal to 0 is satisfied. So which means there is a feasible point and this particular value is positive and you want to maximize it. So what would happen is if C is not equal to 0, then this particular objective value, since it is positive, it will keep on going to infinite. So the solution of a primal problem will be unbounded. If the primal is unbounded, then dual should not exist, which means this particular problem will not have a solution. Essentially, that means there will not exist a y such that A transpose y equal to minus C and y is positive. So that is exactly the second statement. So if the first one is true, then the second statement is not going to be true. Because if first statement is true, then there is no solution for the primal problem, which means the dual also will not exist. So second one will not exist. Now similarly, you can take the other way around. So if the second one is true, which means the dual solution exists, then primal solution should also exist, and primal solution exists only when the C equal to 0. If C equal to 0, then this condition will not be satisfied. If C is 0, then this will be equal to 0. It cannot be less than 0. So the first one cannot be true. Why is this lemma important? That we will see in the coming weeks, where we actually make use of this lemma and derive some other properties for convex problems. But for now, it is sufficient if you understand that only one of them is actually true, and that can be explained from primal dual theorem concepts that we have discussed last week. The next set of problems are the max flow and min cut problems. So these are where most of the problems that we discussed this week will be on. So max flow problem is essentially a one in which you have a network. So V is the inflow. So you have some source, and then you have some connections from this source. Something like this. So all you have is this is a source and this is a sink. So there is certain input to the source V, which is something that we do not know as of now. And then there is a flow from xi to j. So if this is say ith node and this is jth node, the flow that is happening from I to j is xij. Similarly, for all the nodes, whichever combination you take, you have certain xij. All we need to know is we need to find this xij. What will be the flow from particular ith node to jth node? And then there is also a constraints. The constraints are essentially the link capacities. This particular node that we have, you can think of this as some path that follows from ith node to jth node, can I have a maximum capacity of Cij, so that the flow that is happening in this cannot be greater than this particular Cij. That is another constraint that we are having. So with these constraints, what is the maximum flow that you can have here? And of course, the physics also states that there are no storages or anything, so that if you take any particular node, whatever is coming in should be equal to whatever is going out. That is another constraint that we have. So that is a flow conservation constraint. One is a flow conservation constraint, and the other one is a capacity constraint. This is essentially my flow conservation. This is my capacity constraint. So if you see the mathematical statement, what we are trying to do here is maximize B, where V is the input that we are giving here. Since the entire thing also conserves the total flow rate, so if it is V here, this will also be V here. And we are following notation that whatever is incoming is negative, whatever is outgoing is positive. So we are trying to maximize this V subject to the first constraint. The first constraint is flow conservation. So if you take a node I, this particular node, we are doing a summation over J such that xji, Ji belongs to the H. So what does this mean? J is the incoming node and I is the outgoing node. So we take a particular node and enumerate, like list down, take a summation for all the nodes that are having arrows that are connecting to ith node. So that will essentially give me inflow. And similarly, if you do the same thing here, we are flowing from I to J. So we take the ith node and take all the arrows that are going from the ith node to whichever ones they connect, and then take the flows over there. So that is this thing. that will be my outflow. Inflow should be equal to outflow everywhere except the source and the target nodes. At source, what will happen? Inflow will be, I think, okay. At source, the inflow will be, because just with our notation, inflow is always negative. So we consider this to be minus V. And at the target, what will have, you have all the inflow, but the net outflow will also be, the net outflow will also be equal to this particular V. Otherwise, it wouldn't have, like, whatever comes here, and this particular node, if you take what, there is no outcoming that is going out of it. So this should be equal to, this J that you have will be equal to 0. So this particular thing goes off. So this whatever comes up should be equal to V. Similarly for the source node, you don't have any incoming node, so this will go off to 0, and that summation should be equal to minus V. This is incoming and this is outgoing. So this is the flow conservation, and the next one is the straightforward one. Any flow that can happen between any of these arrows should always be less than or equal to that particular capacity of that particular arrow. With these constraints, we are trying to maximize this particular V. So this is the mathematical statement of the problem. The same statement can also be used in different scenarios. Now you can also think of another variant where it's the shortest path problem. So the difference here is, here we are using Cij to be the capacity of that particular link. Instead, you can also think of it as that is a cost associated with moving on that particular node. It's like you can say this is say your home and this is say your school or college, whatever, wherever you are going to, and these are the different roads that you can take. And this Cij can actually be the time taken so that to move from this particular place to this particular place. Maybe these are some bus stops or something. So, or it can be if there are some bus stops, and if you take that particular bus, then Cij is the cost associated for the cost of the ticket or something like that. So if you take like that, then your ideal objective would be slightly different. Your objective would be to minimize the total cost. So then what would you be doing is, you will try to minimize instead of maximization. It will become a minimization problem. And what would be my variable? My variable should be something like whether I'm taking that particular route or not. So if xij will be 0 or 1, 0 if I 1 if I take the route, and 0 otherwise. So if I use this as my objective variable, so I'll try to change this xij so that I will minimize my cost function, where cost function is summation of whatever the cost is associated with that link times whether I'm taking that link or not. So if I take that road, this will be 1 and that cost will be included. If I do not take that road, this will be 0 and that will not be included in my objective function. Now what are the constraints I have? So do I have this capacity constraint now? I do not have any capacity constraints now. It's because each link is essentially the only thing that matters there is what is the cost associated while moving that link. So this particular thing is out of the picture now. The only thing that matters now is this flow conservation. So, but what is the flow conservation now? How would this statement change? So this will, again, it will be the same, whatever is incoming. What is the meaning of flow conservation now? I'll just put summation j just to make it a little easier to understand. Here we are summing over j. J will be the incoming node here. Here j will be the outgoing node. This will be ij. So at every node, you can either go, like if there is an incoming node, which means I've come in one row, then I have to definitely take one of these outgoing nodes. I can't just stay there. Like there is no hotel or something that I can stay over here. It's like that is essentially equivalent of saying there is some storage in the flow network here. That is something that we are not considering currently. That can also be considered later. But let's say for now it's not there. Then what would happen is, if this is 1, then definitely one of them has to be 1. So the sum that you take, again, the sum of all the incoming nodes should be 1 and sum of all outgoing nodes should also be 1 at each and every stage. So if you take the difference, that will be 0 if that particular I is not equal to S, then I is not equal to T. If you take the source node, then definitely you have an incoming, you don't have any incoming nodes. So this will be 0. and the sum of all outgoing nodes, at least one of the part you should be taking, at least one road you will be taking from the beginning. So at that particular road it will be 1 and everything else will be 0. So summation will be 1. So this will be 1. 0 minus 1 is minus 1. This is if I equal to s. And similarly at the target node you will have I equal to this summation equal to 1 and I will be equal to when I is equal to t. So this essentially means there are no outgoing nodes, so the outflow will be 0 and inflow will be 1. So these both the problems are kind of a similar ones. Whichever way you formulate it, for now we are just focusing on how to formulate the problems. There are already tools available to solve all of this. If you give once you formulate it, once you give it to one of any of these linear programming solvers, it will solve the problem. So we are just focusing on how to formulate the problem for now. This is a max flow problem. Are there any questions in this? Yeah. No, you can reverse this too. Then these things will be reversed. Here you'll have plus v, here you'll have minus v. That's it. No, whatever it is, you just keep following the same thing consistently. So here it goes like this. If you see here, if we define in this particular way the way that I have written here, so at the incoming node, what will happen? You don't have any nodes that are joining to this one, right? So this value will eventually go to 0. So the summation of all the values of this one will be v. So this will be 0 minus v. So that will be minus v when you have I equal to s. And yeah. So here, for example, if you take the bus route example, you want to minimize the total cost, right? So that will be a minimization problem. Cost, time, whatever is there, those are the minimization problems. Maximization is like when you have a dam or something that you want to let the water flow immediately to all the villages or something like that. This is the central dam that is your source of water, and these are different canals that you want to, like during irrigation or something, you want to send to different canals. So or you think of like a refinery or something. You have some wells from which you take petrol and all this stuff, crude oil, and from there you have to take it till the refinery. So there, what you want to do is you have to sell the petroleum thing. So like from the crude oil, you have to eventually sell the petroleum. In that entire link, what you want to do is maximize whatever you are taking. The petrol, maximize the petrol output, right? That would be your outcome. So that is a maximization problem. Yeah. Yeah, even the minimization problem, instead of focusing on cost, you can say you want to reformulate the problem saying you want to maximize the profit or something, right? It's about whatever you want. Depending on your objective, you can change it as a minimization or maximization. Mhm. Sometimes you see like what is happening in from when you convert from tribal to dual is one is your dimension is changing. Sometimes it might be easier to solve in the dual space because in the original problem you are solving in Rn dimension. In dual you're actually going to Rm space, right? Sometimes it becomes easier, but what we see eventually is you don't solve separately, like you don't solve only in only in primal or only in dual space. You'll actually solve in both the spaces simultaneously. That we will see towards the end of this particular course. It's like if you remember Lagrange multipliers when we were doing, we are actually solving for both the Lagrange multipliers as well as the variables, right? Lagrange multipliers are kind of for dual variables. So essentially, we will eventually come up with methods that solve both for primal and dual variables, not just one. Yeah, to reduce the because the original problem, as we are saying, is you have like so many points that you have to check. The first order condition, second order condition will not just give you directly the results. So to reduce the number of such points, this can actually help you. So considering both the primal and dual space, you are restricting your search space. Okay. Okay. Can you say which exactly is it? Or do you want me to open the lecture video or something? Or can you share your screen? Okay. But do you have the equation or something where your query is? Okay. Yeah. Okay. So did you understand the part when I explained? Are you clear with this part? How is this first statement equivalent to this primal problem, and how is the second statement equal to this dual problem? Is that part clear? Okay. Then the part one proof essentially tells you, like, basically part one, part two. I don't know which way he followed exactly, but it will be like the first one. Assume this one is correct. Let's say this one is correct. There exists next like this. Then which means the primal statement is this statement is correct, right? And a solution exists for this. Yeah. That I do not know how they got this thing. Okay, you are asking how did they come with this thing? That is there is a bit of proof over there in the last week lecture, right? Uh, I think last week lectures. That's a little you were we were discussing on separating hyperplane concept, and then he actually used that again. That involves some kind of assumptions that I don't know how they came up with, but eventually we'll come up with these things. Yes, the primal variables will become constraints in the dual and reverse. So regarding this lemma, so the first one, as you said, this is a primal. Let's say this is a primal problem. So what we are, if a solution, if an x exists for this particular problem, which means the solution of the primal problem exists. So if the solution of primal problem exists, then its dual, what would be the solution? So if an x exists such that ax is less than or equal to 0 and c transpose x is less than 0, then what will happen to this primal problem? Ax is less than or equal to 0 is satisfied, which means x is in the feasible region, and c transpose x negative. So this is some negative quantity, and you are trying to maximize it. Sorry, this will be negative of a negative quantity, so this will be positive quantity, and you are trying to maximize a positive quantity. And you are saying x is in the feasible region. So what would happen to the solution of primal? It will go to infinite, right? Yeah, it goes to infinity. When primal becomes infinity, this means the dual cannot have an optimal solution. Yeah, if primal is unbounded, then the dual solution will not exist. But the statement here, the second statement here, essentially says you are trying to minimize 0, which means there is a minimum here, and that value is 0, and this is the constraints. So we said the primal is unbounded, which means the dual should have then dual should not exist. The solution for dual should not exist. But this from this statement, this is the dual we got. So which means this is wrong. This cannot exist. So the second statement will be false if first one is true. Is that clear? This is part one. Well, I have an example problem. Okay, then maybe it will be clear. Maybe we'll take the example now itself. Yeah, yeah. I have one problem over for that. So consider this one. or maybe we'll just take an example here directly. So let's say you have so this is 1 and 1 comma 0 and 2 comma 0. This is my feasible region. This entire thing, whatever is inside this, is my feasible region. So how do I represent this feasible region? Uh, this will be something like ax less than or equal to b form. That is clear, right? Till there. Now you have C transpose x. How will C transpose x look? C transpose x is something like C1x1 plus C1x2, right? And B is some matrix. So if you see these points, the equations here will be 1 less than or equal to x less than or equal to 2 and 1 less than or equal to y less than or equal to 2, right? So if you write it in the matrix, so these equations will be minus x less than or equal to minus 1, x less than or equal to 2, minus y less than or equal to minus 1, and y less than or equal to 2. So if you convert it into the matrix, so it will be something like, if you put x and y here, so this will be minus 1 0. The second equation will be 1 0. Third equation will be 0 minus 1. Fourth equation will be, if you multiply this and this, you are getting all these equations, right? This is primal problem. Now let's say, now let us also think of what is C transpose X. Now C transpose X is something, how will it go? It will be something like there is some matrix C here and there is X and Y that are coming here. Okay, just to remove confusion, let's say I will not use X and Y. Let's say X1 and X2. That will be better. Otherwise, there are two X's here and you get confused. This is X1 and this is X2. Let's say here C is 1 and 1. So what will this equation give me? It will give me X1 plus X2. And we are trying to maximize, minimize whatever for this X1 plus X2. What will X1 plus X2 look like? It will be some line. It will be some line like this, right? This will be X1, X2. Hmm. Hmm. Yeah, you multiply with minus on both sides for this part. Then it will be minus 1 greater than or equal to minus x, right? Minus 1 is greater than or equal to, so we just take 1 less than or equal to x, multiply with minus 1, minus 1 greater than or equal to minus x, so that is minus x1 less than or equal to minus 1. Okay, yeah. So this is my x1 plus x2 line. Now depending on the value of x1 and x plus, what will happen? What will happen is, because you will either move this side or this side, right? If you move along this direction, then you are trying to maximize x1 plus x2. If you are moving along this direction, you are trying to minimize x1 plus x2. Now, when we set C transpose X is less than 0, so the first constraint is basically we are saying C transpose X is less than 0. Then what is happening is we are this whatever intercept that you are having when you combine x1 plus x2 is always negative. So this line can only be in this region, something like this. It cannot pass this particular point, because the moment you cross this point, x1 plus x2 will be positive. So so it will be in this region. Now, if you think of this particular ax less than or equal to b, the b here you see there are some positive values and some negative values. And we are saying we need ax should be less than or equal to 0. When will it be next less than or equal to 0? Only when all these values that you have here go to negative, right? So when will that happen? Yeah, so if I just move this to here, third quadrant, then it will be like that, right? So now what we are saying, this is my ax less than or equal to 0, and this is my C transpose X less than 0. Now what we are doing is we are keep on moving this point. So where will the minimum happen? Yeah, somewhere here, right? So minimum is existing. for this particular value. If C transpose X is less than 0 and AX is less than or equal to 0, then a minimum can exist. Now, let's say this is the primal problem. All of this is in primal. Now, if you want to convert into dual, how will we convert? The dual problem is, let me write the primal problem first. So what we have here is minimize C transpose X, AX less than or equal to 0. This is my primal problem. So if you want to convert into dual, minimization will become, oh, okay, we missed out another part here. So this is essentially a maximization problem. Because if you see the original primal dual thing, so it will be like minimize C transpose X, AX equal to B, X greater than or equal to 0. This will be my primal problem. And when you convert it into dual problem, this will become maximized B transpose Y, like greater than or equal to 0, right? Sorry. C transpose X is this particular line. So we can actually move this line here and this side and this side. So you have to think of it in the third dimension. So what is C transpose X giving me? C trans no, C transpose X will give me x1 plus x2. It will give a line only when I project it into 2D. So if this is equal to some particular value z, then it will become a 2D point. Otherwise, it is some in third dimension z equal to x1 plus x2 is some hyperplane. It will give me a plane only when I project it into 2D. It will become a line. And what we are trying to do when we are trying to minimize it, we are trying to reduce this z value. Essentially, if it is close to, if it is 0, let's say if C transpose X is always, if C is always positive, then the minimum that can come is here. Origin, touch the origin, or essentially if this is my feasible region, the line will touch here, it will touch every point. Eventually, when the line comes to this particular point, that's when it will be minimum, right? If I go beyond this, it will be infeasible. So solution will not exist. If I'm here, solution will not exist. And anywhere here, I can always keep moving the line till it comes to this particular point. Yeah, so this is the optimal solution. Now we have another problem now that says that the C is negative. Sorry, C transpose X is negative. So which means this particular C transpose X, whatever you have, is something like if C is negative and X1, X0 is negative, then C transpose X is always positive. Then that keeps increasing. So here we are actually moving in this direction, not in the other direction. Okay, we'll get there first. But this part is clear. So if this is primal, this is dual. It will be a similar thing. So this will be my B transpose Y, but now this will be in a different space. So depending on the number of constraints and say for number of variables, here we have two variables, and the constraints here we have how many constraints we have? 1, 2, 3, 4 constraints are there. Now I will not be able to draw in the dual space because in dual space I will have 4 variables now. So it will be in some 4D plane, like some 4th dimensions. In that 4th dimension also it will be something like this. You will have some feasible region and you will try to move here and there. So what we are trying to say now is if a solution exists in this particular thing, or if a solution does not exist in this particular thing, that is coming back here. So if this particular thing, what we said is this minus C transpose X, if this is negative, what happens is this will keep going on. When you're trying to maximize this thing, it will keep going on in this direction, still satisfying this AX less than or equal to 0. If both the conditions are satisfied, then you will not have a solution at all. So it's like having this whatever you have here as a very big thing, or let's say you have this one. Let's say if this is not finite, this particular thing can encompass the entire space, right? It can keep going on. It can take the entire Q3. If it is entire Q3, then how will you minimize C transpose X? So you keep moving this side, and then it will always be in the feasible region, and you will not have a finite solution. It will be unbounded. Now in that particular scenario, what would happen is if you think of it, this particular variable is your constraint now in the dual space. you're essentially having some constraint that you cannot have, that cannot be solved. So you will not have a solution in the dual space. But the theorem that we have before is, if this is a primal problem, then this is the dual problem that it should have. If this is a primal problem, then this is a dual problem. That is clear. I mean, that is how we define the transformation. Is like, if this is a primal problem and you transform into dual, this will be the dual problem. Yes. Yes, variables are also different. Their dimensions are also different. Now, if you take the reverse statement, that is part 2, I think that's where your question is. Part 2 is essentially assumes that the dual statement is correct. Yes. So you can tell me the logic now. If this is correct, what will happen? What will be the optimal solution if this is correct? Yeah. Yes. So the optimal solution is origin. Okay. Now coming to primal problem. If the optimal solution is origin, what will be the solution of primal problem? No, no. I'm asking the optimal value. If the optimal value of dual is 0, what will be the optimal value of primal? 0. So which means C transpose X should be 0. Then what would be the value of C that satisfies C transpose X? And like, it has to satisfy both, right? X cannot be 0. If X is 0, that is fine. Other than X being 0 also, it should be 0. So the only way is C to be 0, right? If C is 0, whether this condition, will this condition be satisfied? So this will not exist. Okay. Yeah, it is. So if one is true, the other one will actually be false. So essentially, they took the primal statement and they such that the other statement is always contradict the dual one. So if one is true, the other one will anyway be false. As in, oh, where do we use this thing? You are asking where we use this Parker's lemma. There are some theorems where they actually use this. We will see maybe in ninth week or something. And once we have tangent codes and stuff, uh, it's essentially kind of without, see, if you know that there is a solution in this particular form, then you already know that this particular solution does not exist. So it will be useful where like in the initial weeks we discussed, like without actually solving, you'll get to know whether a solution exists or not in the first place, even before solving. There is one example problem I'll show you there where you can actually use this lemma. It's not, it won't help you in solving everything, but if you know one thing, you know that the solution will not exist for other. So that way you'll reduce the number of search space. I mean, the number of points that you have to search for. That's the whole idea is that how do you reduce the number of points that you have to search for before coming to the optimal solution. Everything we do is for that. Yeah. So the max flow problem is clear. The next one is the min cut problem. So this is also very similar to the max flow. It's actually the same, just the max flow problem in the dual space. We take the same problem now, but now instead what we do is we have the same source and sink, everything is the same. But then now the problem is we try to cut the edges in such a way. Say I want to cut it something like this. And we try to determine whether the flow from source to sink is entirely cut down because of this or not. So essentially we try to cut it in different ways. You can cut it here, you can cut it here, you can cut it here. These are different cuts, like C1, C2, C2, C3. These are the different ways you can cut this particular network. So what we are trying to do is when we cut this particular network, even we need to cut it in such a way so that whatever the flow that is happening at these cuts that are happening should be minimized. You can think of this like, let's say during COVID or something, you have a supply chain. This is from China or something, and this is some place in your factory or whatever. You need some product to come through this particular way. So because of some lockdown restriction or something, some of these parts will actually be intercepted by during that particular transit. Some of the parts will be intercepted. So you want to know if for suppose this particular town is under some kind of quarantine or something, so that goods cannot be traveled in that particular place, then how do you assess the impact of that thing on your whole network? So if you what you do is just cut that thing and see how much flow is happening from that, and that is the flow you have lost. So what we need to do is identify the cut. You can make several cuts. Out of all those cuts, what is the cut that will give me the minimum flow? I mean minimum capacity. So if the capacity of this is Cij, so by cutting this edge, I'm getting a loss of Cij. If I cut this one also, let's say this is, let's put some numbers. This is 0, 1, 2, 2, 3, 4, 5, 6. So if I make cut 2, the losses I'm incurring is C13 plus C14 plus C24 plus C25. So this is the capacity loss I'm getting by cutting through C2. Similarly, if I cut through C1, then it will be C01 plus C02. So what we are trying to do is, out of all these 100 different, whatever different cuts I can make, what is the cut that will give me the minimum loss in the capacity? And to solve that problem, okay, just another point here. So even here, if you see, when we are trying to maximize the flow or something, the main point here is, what is the one that is limiting your entire flow is there will be some bottleneck inside the entire one. That will be the weakest one. It's like they say, the whichever one is the weakest one, whichever has the lowest capacity, or not to put it in lowest capacity kind of thing, there will be some particular path that will be the bottleneck, which will prevent, which is the main, if you recollect your, I don't know, if you're from manufacturing, you might have done some courses where you have an assembly line kind of a project where you have some goods moving from one work center to another work center. There will be one work center where most of the things will get stuck, and that will be the critical one. Why is it critical? Is because any step, for example, if you have if you want to manufacture something, there is some particular good, there it can go through 100 different steps, but eventually it has to go through some painting, let's say car painting or something, and only after painting you will get the final product. Now if any product, whatever you do, eventually it has to come to painting, and only from there it will go to the output, and you have just one painting station, then that will be a bottleneck, because if something happens here, then everything goes wrong. So the limit, if the painting can only do 100 goods per second, per minute or per day or something, 100 goods per day, but you have other equipment which are doing say 1000 goods per day, the maximum flow that you can get is limited by this painting. It will be only 100. So what we are trying to do in this entire max flow problem is trying to identify this bottleneck which is causing the limitation. So once you identify this bottleneck, your problem is solved. So the whatever is the production capacity of that bottleneck thing is, that will be the maximum flow that you can achieve in that particular network. In a similar way, we are trying to do here as well. So what we are trying to do now, even in this problem, here when we are cutting, when we are trying, we need the minimum change in the capacity is the same, right? So if here also, instead of saying maximum flow, you say you identify the one with the minimum productivity. So if you, this is 1000 per day, this is 500 per day. When I cut this particular equipment from the entire loop, the loss I am incurring is only 500 per day here. But when I cut the painting of the loop, then the loss I am incurring is 100. So that will be the minimum one. So even by cutting and doing the trying to minimize the capacity associated with it, I'm trying to find the bottleneck. And in the other way, when I try to maximize the flow, also I'm trying to find the bottleneck. So eventually I'm trying to find the same thing. So this is more elegantly said, like this is a primal problem. The other one will be the dual problem. So whatever solution you're getting is the same thing. And that is because in both ways, we are trying to eventually get to the bottleneck. How do we identify the bottleneck? That's the whole point in all these network problems. So how do we formalize this mathematically? So we put some label Wij to each of the edges here. So when I cut a particular edge, if my cut is touching that particular edge, Wij will be 1. So we are defining two sets S and S prime, where S is a set. So essentially when we cut, we are dividing it into two halves. So one half we are calling S, and the other half we are calling it as S complement. So S is a set that is containing the source node, and S complement is a set that is containing the sink node, or let's say target node. So that is US and UT. So now we have some other variables that are coming. So first is the W variable, where Wij will be 1 if I belongs to S and J belongs to S prime. What does it mean? So if I cut this particular one, I should have the incoming from the source one and the outgoing from the target node. Only then that particular thing will have a weightage of 1, and that capacity is what that should be included. So if this is the cut I made, if I want to take Wij here, I will be in the source node and j is also in the source set. So both I and j are equal, so Wij will be 0. So that particular capacity will not be included in the objective function. So if you keep doing it for all the edges, so we are summing it over all the edges. So only the edges where the cut touches will have the capacity included. So the objective function will give me the total capacity that is reduced by cutting along that particular arc, whatever arc, C1, C2, C3, or whichever one that you have taken. And the constraints goes like this. So now we have a problem that whenever we are cutting, we need to separate the source and sink. How do I achieve that? So if, we define another variable now, u. So what does this u say? Now I have certain number of nodes. I have to split them into two categories. That is, whether does it belong to S or S complement. So what we have defined is a new variable that will be 1 if it belongs to set S and 0 if it belongs to S complement. So we have done that as well. So now the other problem is we need to, whenever we are cutting, we are dividing into two halves. So one half should contain the source and other half should contain the target. So how do we ensure that? To ensure that, we need to put this extra constraint such that US minus UT is greater than or equal to. When we do this, what happens is US is 1, S is that particular node should belongs to, S is the source node. Since it belongs to the source node, this will be 1. Since it belongs to the target node, if it will be 0, so this will be equal to 1. So why are we doing this? So for example, if I do not have this constraint, what will happen? Then both the source and sink will come in the same thing. Then US will be equal to 1 and UT will also be equal to 1. Then it will be 0. US minus UT will be 0. So you can have US UT and US minus UT. Put it this way. This can be, both of them can be 1. Then my US U minus UT will be 0. If both of them are 0, then also 0. Something like this. So now out of all these four scenarios, I want only this particular scenario. Remaining ones I do not want. So I have to explicitly mention that in the constraint, and that's why that we are keeping this particular constraint. US minus UT greater than or equal to 1. And what is this constraint? Uj minus ui plus wij greater than or equal to 0. This is also the same thing. So not the same thing. Essentially, it's like the flow conservation thing we have. So when I cut at this particular node, I need to ensure that wherever I am cutting, one node should be from the incoming and the other one should be the outgoing. So if you take the value of wij in that particular value, so if you can also write that particular constraint as wij greater than or equal to ui minus uj. So again, you can think of it this way: ui, uj can have different values. If both are belonging to the like whenever I made a cut such that both are belonging to the same set, then that is of no use to me. So this wij will be 0, and you can have different scenarios. If both are belong to 1, wij should be 0. If, for example, one is belonging to set 1, the other one is belonging to set 0, then this will be 1. And if the both are belonging to 0, then it will be 0. Let's say the first node belongs to this particular set, this particular set S complement, and uj belongs to S. Then what will be the value of wij? If I just define wij equal to ui minus uj, this will be 0 minus 1, this will be minus 1. Now what we want wij to be is, whenever I cut a node, I should have one incoming node and one outgoing, like one from the set S and the other from the S complement. Only then it makes sense. Like that cut will disrupt the flow from source to target only when one node is in the source and other node is in target. If both the nodes are in the source, or I mean, if you cut it in such a way that both of them are in the same path, like if this J is here, then there is no point in that, because that will anyway not reduce the total capacity of this particular network. So we want to avoid such instances. So that's the main point, that we say that wij can be only one of these two things. So wij can be this, can be this, can be this, but cannot be this one. How do we enforce that? We say that wij is always greater than or equal to 0. And then when this particular scenario happens, when one of them is 1 and other one is 0, this value becomes 1, because you see, and that also satisfies this constraint. And what we are trying to do is we are trying to minimize the, so what is the variable here? The variable is here is this one. The capacity is a fixed one. And we are trying to minimize Wij. So what it will do is it will try to minimize Wij, so it will eventually come to 0 everywhere. Only the points where this cut happens will become 1, and it cannot be any other value because Ui is 1. If you forget about all the math, what this essentially says is you are trying to minimize the total capacity subjected to two constraints. What this constraint says is source and target should be in different sets. And what this first one says is your Wij, whatever you are taking, should always be binary. So that whenever you cut it, that cut whatever you are making should be in this particular way. How should I write that? So what will happen when you keep doing this? Eventually, you will reach a point where you will touch the bottleneck. And once you touch the bottleneck, that will be the minimum capacity that you can get. And that's the solution we have that we get even by solving the max flow problem. So both the max flow and min cut will eventually give the same physical output. I mean, the one that you want to identify, the bottleneck. Okay, is this clear or are there any confusions in this? No, no. We solve this problem and Wij will come as a solution out of it. This is a solution. Once you solve this problem, formulate this problem and then solve it, this is a solution you will get. Sorry, I didn't get it. Can you repeat? Yes. Hmm. Yes. Wij is not the output. Yeah, Wij is the solution in the sense this is a variable that we are trying to optimize. So it's like the same like in the previous problem. We are trying to maximize V subjected to so many x values, right? X is what we are trying to vary. Similarly, here we are trying to vary W, but not just W. We are trying to vary U and W, but U is not appearing in the objective function. That's it. But still, it is there in the constraints. No, US is basically it's a function that tells you whether that particular node UI. Basically, if you say UI will tell you that particular ith node whether it is in like whenever you are cutting it, it can either belong to the set that has the source in it or it can belong to the set that has target in it. So to differentiate between these two, if it belongs to the source, this value will be 1. If it belongs to the target, it value becomes 0. Mhm. Yeah, that's why we are putting it in this way. So when you put the constraint that US minus UT is greater than or equal to 1, then and we are saying US and UT are just binary variables. So you can have out of this all scenarios, the only scenario this can be greater than or equal to 1 is US should become 1 and UT should become 0. So definitely US will become in the source one. I mean, it will split like that. Okay, you're thinking of it as a continuous one, or just to be easy, just think of it as a binary one. It can either be 1 or 0, nothing in between. Let's say that will be much easier to think, right? Yes, yes. Initially, what it will do, it will let's say initially everything it will give zeros. All the states will be zeros, and then what will yeah, then it will keep updating it, right? Once you cut here, like during in the cutting edges, this W will be 1. Now once W becomes 1, then UI minus UJ should become 1. So it will keep one of them to be 0 and the other one will become 1. So this will become 1, this will become 0. You will get updated. And you keep doing it, keep doing it. Eventually all of this will become 1s and all of this will become 0s and you will have the W's correctly. Understood? Okay. This is again the different form of Farkas lemma, but again, you can also think of this same as the primal dual thing that we have. So here also we have a matrix M cross N and C belongs to Rn. Then both the small c here, little c. So for all x such that Ax less than or equal to 0, we have C transpose x less than or equal to 0. The only difference, previously we just have less than 0, now we are having an equality symbol as well. So it can be 0 or less than 0. And then there will exist a lambda belongs to Rm such that lambda is greater than or equal to 0 and A transpose lambda equal to C. So if you think of the first problem as something like this, maximize C transpose x, Ax less than or equal to 0. And you can think of the second problem as if you take this is the primal, then the corresponding dual will be minimized becomes maximize becomes minimized. This constraint will become the objectives, variables, and whatever is in the objective originally comes in the constraints here. So both of these are primal duals. If you follow the same logic as before, if the first one is true, what will happen if this particular statement is true and C transpose is negative, then in order to maximize this, when you try to maximize a negative quantity, the maximum value that you can get is this being equal to 0, which is equal to this particular one. So the objective will be the same. So if this solution exists, then this solution will also exist. So if this is true, this one will also be true. So previously we said only one of them to be true, but now if this is true, this will be true. If this is not true, this is not true. This is very similar to your strong duality statement. So all of these statements are essentially the same thing. If you understand the primal dual concept, you'll make all of these statements from there directly. Next, the most important one is the concept of complementary slackness. So this is clear. The number of constraints in your primal are essentially becoming the variables in your dual, so that this number will be equal. And similarly, the number of variables in primal will be the number of constraints in dual. I have not written it because let's put n vice versa. So if a particular constraint holds strictly, then the corresponding variable in the other will be 0. What I mean by strictly is, let's say we have a constraint Ax less than or equal to b. Now holding strictly means Ax equal to b. Or to put it another, whenever we have this, previously we used to write it as Ax plus s equal to b and s greater than or equal to 0, something of this sort. So what we are saying now is s equal to 0. When this happens, we call that holding strictly. When a constraint holds strictly, then that particular s will be 0. What is this s? This s is basically my variable in the dual space, right? So that is what this particular statement says. That is the entire thing of the complementary slackness. So if the variable here is strictly holds, then the constraint will be 0, and reverse. If the variable in the dual space strictly holds, and the constraint in that particular primal space will be 0. So what is the meaning of a constraint being 0? If you recollect, whenever we have two types of inequalities. We have equality, we have two types of constraints. Either we have something like less than or equal to, or we have equal to. Whenever we have a less than or equal to, it represents a region. So if you think of it in a plane, when we describe it, so if you have a circle and my inequality goes something like x square plus y square is less than or equal to r square or something of this sort. Whenever I said less than or equal to, it means this entire region. Now, if I just say x square plus y square equal to r square, then it means only the boundary points are included. So that's the difference between equality and inequality that we have already seen before. So now what we are saying now is whenever you know that a particular constraint is 0 in the primal space, then in the dual space, instead of searching over all the points, you have to search just the boundary points. That's what the complementary slackness condition says to you. Mathematically, you can say that if omega p is your feasible region in the primal space and omega d is in the dual space, if x star is optimal for primal, this implies there will be a lambda star in omega d such that this particular constraint will be satisfied. And it also says that if this lambda is 0, then the corresponding constraint will be strictly whole. So that particular this is your constraint that the constraint will be A transpose y greater than or equal to 0. but we are saying that lambda star is particular lambda star is 0, so that particular variable is 0. So this greater than or equal is not strictly held. So this becomes A transpose phi greater than C. When this is greater than C, this implies X j star equal to 0. Or the other way around. In the original problem, we have Ax less than or equal to B. Let's say something like this. If it is strictly whole, Ax less than B, if we know that it is less than B, then definitely lambda star has to be 0. There is no other way. They are the optimal solutions, just to differentiate between the normal variable and optimal variable. So why after doing all of this, the main thing that we get here is these two equations. These are the main points. What this complementary slackness tells you is one of them have to be 0. That can also be written in this particular way. So when you take this product of two quantities to be equal to 0, it means that one of them have to be 0, but the product will always be 0. Both of them can be 0. That is also a special case, but the product should always be 0. If Ax equals to B, Ax equals to B means in the primal problem we have a strict equality. Then lambda star we don't have to worry about. Lambda star may not be 0. But if lambda star is equal to 0, it's the same thing. In the other, so this is the constraint. Let me write it in this way. This is the constraint in the primal problem. This is the dual variable. This is the constraint in the dual problem, and this is the primal variable, corresponding primal variable. So whenever you have these two are additional equations, right? And these are not linear equations. So essentially now you see previously all we have is some Ax equal to 0 or Ax equal to B or something of that. All of them are linear equations. But now when you have product of two things and this x star and lambda star, it becomes non-linear in x star and lambda star. So you have to put different conditions. So you have to assume that, okay, let's take x star equal to 0 and A transpose lambda star not equal to C, or different cases. X star not equal to 0, but A transpose lambda star equal to C, or both of them equal to 0 is something. All the different cases you have to try, and for each case you have to get, you assume x star equal to 0, and then this is not satisfied. So you have to find lambda star differently from another equations. Or if you say x star is not equal to 0, then you can directly use this equation to find lambda star, and you have to use a different set of equations to solve for x star. So solving equations will become a little difficult. So that's where the nonlinearity comes. So even though the problem is linear, once you consider both the primal and dual spaces, so if you consider only the primal space, we had something more of linear sort. But when we want to consider both of them together, we ended up with some nonlinear equations. So how do we solve these nonlinear equations systematically, or how this entire thing can be put it in a framework where you can solve? That's where the next step comes. That's the KKT conditions that is in your next week. I think yeah, week 8 or week 9 is where the KKT conditions come. Is this clear up until here? Complement slackness, all it says is if a constraint holds strictly, that is, if we say that it is strictly less than 0, that there is no equality, like this constraint is not strictly satisfied, or to put it in other words, there is some slack that is left. So okay, I think I might have said something wrong before. Sorry. This is strictly greater than 0 is what we call as strict. So there is some particular slack that is left in this particular constraint. Then it means that particular slack, so it's the same thing. So this particular thing, if a slack exists here, then the corresponding variable in the dual will be 0. Or if a slack exists in the dual space, then the corresponding variable in the primal will be 0. Those are put it in some other form here, but both are equivalent. This and this are equivalent. Okay, are there any questions in this? Yes. So physically what it means is like you have supply and demand. Let's say say this is the LHS is my supply and this is my demand. Oh, sorry, should be the other way around. So this is my supply, this is my demand. What I want is I should always want my demand to be less than or equal to supply. normal rate. So whatever the difference is, the difference between the supply and demand is your slack, is essentially your buffer that can help you protect when there is something that changes in the demand or something like that. So all we are saying now is this buffer is what we are calling a slack. So if that particular slack is zero, so suppose the slack is zero, what does it mean when the slack is zero? It means my demand is equal to supply if slack is zero. If demand equals to supply, then I don't have any control in that thing, right? I can't do any optimization there. The constraint, whatever I'm left with, that is the thing I can, even if I want to minimize, maximize something, I can't do anything there. But for example, there is some slack, then there is some scope for doing something. Actually, not in that particular way. Okay, maybe it conveyed something wrong. Okay, let's think of it in a different way. How do I put it? A simple example. If you think of this, mm, okay, maybe I should take some example. So just take the demand and supply example. So if you have some slack, so what we are trying to optimize is, let's say you want to minimize the total cost or something. Your slack, okay, the name essentially means that you have a constraint, but then you are not actually satisfying the constraint. You still have, see, ideally you would want demand equal to supply, right? That, that is the ideal one. But then if you keep doing that, then you will not be having any advantage. Like if something goes wrong here or there, maybe your model is wrong, or maybe demand suddenly increase, then you are out of business. So I don't know. I think they use it literally cut some slack or something like that, which means you relax your constraints. So you relax your model. You don't assume that demand will always be equal to supply. Instead, you assume your demand is always less than supply. So essentially, you relax your supply, like you put more money and supply more. Even if something stays in the inventory, that is fine. I do not know the exact literary meaning, but the way in the constraint it holds is this. It's like some buffer that you can keep. The slack variable essentially reflects the buffer that you have in the constraint. Even if the constraint doesn't hold strictly, then you're like, even if it is not equal to, even if it is less than, still you are safe. Even if it is equal to, this is when this s is not equal to, s is equal to zero, that's when you have problem. The moment s equal to zero is the constraint that is most critical, and you need to take care of them. Complementary slackness is different. Complementary slackness is essentially saying that whenever you have whenever you have this particular constraints, something like this, which means when you have s not equal to zero, then the corresponding thing inside the dual space will be zero. You can also think of this as when you have the orthogonal matrices and all this stuff. You say complementary is if one is zero, the other one is not zero or something like that, right? So both of them are like, I mean, that's the word they use it for it. Supplement is like they support each other, and complement is like they oppose each other. So if one of them is not zero, the other one will be zero. Okay, I usually do not do it that way, so I'm okay. Yeah, I'm not aware of the reasons why they kept this name, but the thing that you can kind of easy to remember is the way that I understand it is whenever you have scenarios or whenever you have some constraints, like for example, if you take of this example, the painting example that I have. So here each of this is this 100 is basically the maximum thing that it can take. 1000 is also the maximum. Each of this equipment, whatever number I gave here, is a maximum that particular mission can take. Now, whenever one of these missions is completely used up, so which means the actual production is equal to 100, then that means the slack in this particular variable is zero. So you cannot relax in this particular one. Yeah, but for the other equipment, it's not like that. So there is still some scope for improvement there. So there you have certain slack. So you can relax them. That's what they say. I mean, that's what I understand. Yes. So so that is where your optimization comes. So which means you cannot directly take this value. You need to do an optimization problem. You need to solve for it, and then you have to get to the value of what this actual value is. It will change. We need to solve this. Yeah. So wherever slack is not equal to 0, then those are the points that we need to solve for. And how do we determine that points is in a different way. So instead of trying to solve in the primal space, if you go into the dual space, so essentially here if you say this is strictly less than this thing, so slack is not equal to 0. So now what we do, we go into the dual space. In the dual space, we solve for the corresponding lambda. If that lambda comes out to be 0, then it means here we'll get to know that particular slack is not equal to 0 here. So that is something that we can solve for. So that is mathematically put it here. If you mathematically say that lambda equal to 0, or like if this is equal to 0, then this is not equal to 0, or one of them is 0, you just multiply both of them and put them equal to 0. That is just a mathematical way of saying it. Okay. Yeah, these are the concepts. Okay, we'll solve the problems now. We have around, yeah, we have time left. Okay. Yeah. So first question is, you have a problem to maximize the flow in a particular directed network. Then the source is the one that has the least number of edges. It's a statement true or false. Can we say that source has the least number of edges? I can have a network like this, where the source has 3 edges, but some intermediate nodes have just 2 edges, and target has 3 edges. I mean, I can always construct a scenario where the source can have number of edges greater than the remaining ones. So, like there is nothing that restricts that the source to have certain number of edges or something. This is false. This we have already discussed. So in the maximum flow problem, we have the different constraints. The first constraint is a flow conservation, that every node, whatever is incoming, should be equal to whatever is outgoing. Flow capacity and non-negative flow constraint. This non-negative essentially says that flow happens only in one direction and not in the other. Like here we say it's that it's a directed network, which means flow, like in water flow networks, so it flows from high pressure to low pressure unless you have some pumps or something. So in the problem that we discussed, in the way that is formed, whenever I say directed network, there's a unique, so it flows only from I to J, not the other way around. So that gives you the non-negativity constraint, flow capacity constraint for each link, and flow conservation is that each node you need to have incoming equal to outgoing. So all these constraints are satisfied. Yeah, maybe you should answer this. So you have a directed weight graph, and the shortest path from a source vertex S to a destination vertex T. Suppose we increase the weight of every edge in the graph by 10 units, then the shortest path may change in the modified graph. So it's like saying you want to move from your, let's say, wherever your home is to your college through some bus route, and all the bus routes, the price increased by 10 rupees. So will the optimal route change? So hmm, may or may not be the same, right? So some routes might be connected to, like for example, if you're following one route, you might have to go only through 2 buses. If you follow another route, you might have to go through like some 10 buses. Now, if it increased by 10 rupees at each and every bus that you go, First route will increase by 20 rupees, second route will increase by 100 rupees. So you can have something like this. This is something, and you can have a scenario like this. Let's say originally this is 1 and 1, all of them are ones. So first route, the shortest route, this route will give you 2, and this route will give you 4. Now if I increase both of them by, okay, this is a very bad example. Maybe let's say this is, no, if you think in that way, if you think in terms of equation, then what are we changing? If you think in terms of equation, what we are changing? Are we changing the constraint or are we changing the objective function here? Weight is a cost. Yeah, the cost value is changing. So the objective function will change. So the objective function itself is changed now. So it's not ax less than equal to b. It's in the objective function, the c transpose x, where we are getting, where we are having some changes. The c is what we are changing. Yeah, the c is what we are changing. But then if which we like in the transformation of objective optimization problems, we have seen if you are scaling an objective function by some positive constant, then it's of no problem. If instead of saying increase the unit by 10 units, if I say multiply everything by 10 units, let's say you move the same routes, instead of taking in rupees, if you take the ticket prices in dollars, it is just a conversion factor there. That wouldn't affect as long as your routes are within the same zone. Like everything is, whether you do it, solve the problem in rupees or you solve the problem in dollars, you're going to get the same shortest route, because that is just a scaling factor. But when you're doing an addition here, your objective function, it doesn't follow that same transformation. So this is actually true. So the shortest path may actually change in the modified graph. And that essentially depends on, so if the previous shortest path is, let's say the shortest path cost has the objective function, let me write in the objective function. The objective function is maximize ci times wi, where wi equal to 1 on shortest path and 0 otherwise. Or okay, this will actually confuse you more. Let's take this direct, something very simple. Just to previously the shortest path is c1 times c1 plus c2. Now what we are doing is that there are there are two paths, c1 plus c2, and there is another path, c3 plus c4 plus c5. So this is like, this is 0 1, this is my target node, this is a source node, this is c1, this is c2. So this is path 1, and then there is another path. So this is c3, c4 and c5. So initially, let's say the objective function, this is the shortest path, this is some longer route. Now if I increase the price by 10 units, so this will become c1 plus c2 plus 20, this will become, yeah, plus 30. So this is less than this and this is less than this. So this is a clear one. Okay. And how do I construct a scenario where it will become greater than the other one? Sorry. Yeah. So can I construct a case where that doesn't happen? Can we construct a scenario where this particular inequality reverses? So let's say something like this. So there are three costs here, and you have C1 plus C6, C4 plus C5. Let's say this is a one. This is the shortest path. Let's say initially this is the shortest path. Now if I increase everything by 10 units, so this will become plus 40. Now I can also do C3 plus C4 plus C5 plus 30 if I increase a second time, if I increase everything by 10 units. So now if you compare these two, we cannot say which one will be higher or lower. Depending on the actual values of C1, C6 plus, if this particular C1 plus C6 plus 40, if that is less than C3 plus 30, then we will still have the same shortest path. Otherwise it will not happen, right? Normal shortest path is C1, C6, C4, C5. I mean, we do not know the cost, right? I did not put the actual values of C1, C2, C3. If I put the values, depending on the values, you'll have the shortest path. It's not how many connections you have, right? The cost will be different. So depending on the relative value of these connections, by increasing 10 units, maybe one path is actually more economical than the other path. This example will work then. Okay. So here the next one is about cycles. So if I have a shortest path problem where every edge has positive weights, then the shortest path from source to destination may have cycles. Can it have cycles? Cycles is basically you're just taking loops. You start from point, you go somewhere, and eventually come back again. Or let's not go to the starting point, but say you go somewhere else, and then you keep looping here, something like this. So this is your cycle. So what we are saying is, if all the weights are positive, can I have cycles in my shortest path problem? No. Okay. Why? Yes. So your cost will always increase. Yeah. Your cost or whatever time will always keep on increasing. So you can always take the first loop, and like instead of going to the loop, you can always go outside the loop, and that will reduce the shortest path. So optimization will come out of the cycle anyways. This is false. Okay. So this is one problem. So where you have two sources, P1 and P2 are sources. D1, D2, D3 are the destinations. T1, T2 are something in between. So these are the costs associated if you take that particular link. If you go from P1 to T1, it will be 3 units. P1 to T2, it will be 4 units. So these are some costs associated with that particular links. So we need to formulate the optimization problem to minimize the total cost to move from source to target, where numbers on edges are the costs associated with taking that particular link. So essentially, I want you to write down all the equations in the form that we have written before so that you can solve them. So where do I start? So what will be my equations? What is the variable that I'm trying to solve? So what kind of problem is this? Is this a maximize flow problem or shortest route problem or min cut problem? What kind of problem is this? So what are we trying to do here? Yeah, so it's basically some kind of shortest route problem, right? So what is the variable that I'll solve here? How should I formulate the problem? What should be the variable that I will be solving for? The costs are already given. So what we need to find is how much material we are going to transfer through that particular route. So there are some 1,000 units that are coming to P1. So you can decide how much of this 1,000 units will go along this route and go along this route. For every unit, you are spending, let's say, 3 rupees or something. Or that's not actually practical. Maybe you can think of it in other way. Let's say this is there is some distance from P to T1. Like physically, this is some point A, and this is some you are moving from some place A to place B, and this is like per mile of the road that you are traveling. This is the amount of charge of fuel price or something. Then depending on the number of miles, this will keep increasing. So how do we choose which path to take? Like eventually, how should I change my plan? Should I go like this, say from say Chennai to somewhere in Kerala, and from there to somewhere in again go to Hyderabad or something, or choose some other path? Which path should I take? How do I formulate the problem? Anyway, so but whichever way. So how do you propose? So you are saying what is the variable that you are trying to solve? So whenever we say formulate an optimization problem, what are the three things that we need? We need to first decide what are my variables are, or to be precise, let's say decision variables. What are my what is my objective function, and what are my constraints? These are the three things that we need, right? First, we decide what the variables are, and then we formulate the objective in terms of those decision variables, and we formulate the constraints also in terms of those decision variables. Once you have all these things, then our optimization problem is formulated. So what are the variables now? What should I consider as variables? Instead of putting this one, I just put some numbers here so that 3, 4, yeah, no numbers, 6, 7. That will be easy. No, what would be my variables? So what am I trying to do now is to find the path that will give me the total cost should be minimized, right? So which means whether should I take this path or this path? That's the question. No, no, do not go into solve. Do not try to solve the problem. We are not focusing on how to solve the problem. How do I formulate the problem? What is my variable? Yeah. So basically, the variable is how much should flow through this particular point. Like whatever the flow that is happening from P1 to T1 is my variable. So x13 is one variable. Can I write it like that? X13 is whether X13 is basically telling me if I take that particular route, X13 will be 1. If I do not take that particular route, X13 will be 0. Yeah, 3 is fixed. 3 will not change. This 3 is the cost. Okay, maybe you're confusing this nodes and cost. Maybe I'll put different. I'll put ABCD for nodes. That will be easy. Say A, B, C, D, E, F, G. So my first variable will be XAC. So from A to C, it will be 1 if I take that route. If I do not take that route, that will be 0. So like that, I can have different variables like XAD, XBC, XBD, XCD, CE, and CF. Similarly, XDF, DG, and XEF, FG. So all these things, any of these X can be 1 or 0. So these, I need to find the values of X such that in the shortest path, whenever I have the shortest path, all those X's will be 1. So if just a case, if let's say this is the shortest path, If this is the shortest path, then this particular XAC will be 1, CF will be 1, remaining everything else will be zeros, right? So how do I solve it now? I mean, what is objective now? So I've identified the variables. So objective is minimize. Yeah, what is the total cost now? No, no, no. So what will be 3 times XCAC? No, okay, 6 times XCF. That is, it will be everything else, right? 3 times XCAC plus 4 times XCAD plus B2C is 2 times XPC. If you see, if you take that particular route, this will be 1, cost will be added. If you do not take that route, X will be 0 and cost will not anyway be added into that. That's why we are choosing X in such a way that it will be 1 if we take the route and 0 otherwise. So it will keep going like this. 5 times XPD, similarly 8 times XCD plus, uh, sorry, we'll include everything. 7 times XCD, okay. What are the other terms that I have? DF is 4 times XDF, DG is 9, EF is 5. So this is my entire objective function. So objective function is clear, variables are clear. So now what are the constraints? No, supply is equal to demand. There is nothing there. This is 2200. Here also we have 200. Yeah. So at each node also we have to apply conservation. That is what you're trying to say, right? How do I write it mathematically in terms of whatever variables I've defined here? So I'll take one node. Let's say we take P1. At P1, what should I write? What is incoming at P1? No, that is fine. But the cost. So sorry, not the cost. How should I put it? So when we were discussing, how did we define this problem? See, when we define these are the constraints, so we are trying to minimize this sigma Cij Xij, and the constraint is this sigma Xji minus sigma Xij should be equal to these values. What is this sigma? What is this Xji? J is the incoming node, I is the outgoing node, right? So if you see that now here, which question? Fifth question, right? If you see that here for P1 there are no incoming nodes. So sigma Xj will it's a source node. So for P1 node it will be 0 minus whatever is outgoing. What is outgoing? XAC minus XAD. These are the outgoing nodes. And this should be equal to, since it is a source node, it will be equal to minus 1. Now, if we take P2 node, that will also be similar. XBC minus, that is also a source node, so that will be minus 1. So let's take this is for P1, this is for P2. Say for example, if I want to take for T1, what will it be? Yeah, what is the input for this T1? No, no. When you write 3, then it is a cost multiplied by that one. But constraints are basically saying input should be equal to output. Cost doesn't come here. So it's just so XCAC plus, no, BC is also coming, right? Yeah, these are incoming nodes. Now outgoing nodes minus CE minus CF minus D should be equal to, no, there is no source or sink for T1. T1 is an intermediate node. So whatever incoming should be, whatever that comes here should go out. So if you come to T1, then you should definitely take one of these and go out. So this should be 0. Incoming should be equal to outgoing. Yeah, inflow equal to outflow, so that will be 0. So the same goes for T2 also. If you take T2, what are the incoming ones? So we have AD, CD, XCD. These are the incoming nodes, and outgoing nodes are just XDF and XDG. That will also be 0. Now these are your intermediate nodes. Now what about D1? XC is incoming. Yes. Outgoing. Hmm. No, you don't write minus 800. That is equals to your 1. 800 is a different thing. 800 just says that that many units can actually go. If you take 1, then 800 units can go through that. That's it. Yes. Maybe this is some system. Let's say this is all of them are 1. Maybe that will be easy to understand. Okay. Now D2. D3 is the last one. You just take XFC plus GC should be equal to 1. Now if you see, all these equations are linear equations in your variables. So you can construct them as a matrix. All of these equations you can write as Ax equal to B, where your A will be, where your X is all these variables written down as column vector. So if I write it down, how will it be? So if I write down X, X will be all these variables. You just write in one column vector. So it will be something like XAC, XAD, BC, BD, CF, oh sorry, this is EF and FC. So this is your X. Now how do I write my A matrix? So you take all these equations and then you have to write the matrix. How will that matrix look like? If you take all these equations, essentially they will be multiplied with this thing. So A will go something like, what is the coefficient of AC? So we'll just stick like B greater than or equal to 0. In our standard form, we have C transpose X, minimize C transpose X, AX less than or equal to B, X greater than or equal to 0, and we have A is full row rank and B greater than 0. Just to be consistent with that, you just multiply this with -1. So XAC coefficient should be 1. What is XAD coefficient? That is also 1. Is there XBC in the first equation? So that will be 0. XBD will be 0. CD is 0. CE, CF, DF, DC, EF, and FC. All of them are 0. Right? Yeah. Now you have 11. I haven't counted. It's 11. And how many rows? No, no. How many equations I have? 1, 2, 3, 4, 5, 6, 7 equations. This will be 7 by 11 matrix. This will be B is 1. So this is just the first element of them. What is the next equation? Next equation is this. XAC you don't have anything. XAD also you don't have anything. X, BC and BD you have some values, so that will be this equation. And the third equation, XAC you have, XBC, XAD is not there, XBC is there, so that will be 1, XBD is not there, XCD is there, XCE is also there, CF is there, that's it. You got it right? Yeah. Now we can do the similar thing, or do you want me to do, or maybe quickly do it? You have time? No need, no? You understood the concept. Yeah. So like this, if you write it, so it will be a 7 by 11 matrix, and here you also have a 7 by 1 matrix. So this is 11 by 1. So when you multiply this and this, you'll have Ax less than equal to B form. Sorry, Ax equal to B form. And what is my C? I'm not written C here. C transpose is what my values are. These values are 3, 4, 2, those values. The cost values, yes, 3, 4, 2, 5, all those things once written. Those will be your C values. So now you have it in your standard form. This is what you will give as input to your solver, whatever software you're using, and that it will solve them. Yeah, so that is clear. Now the next question. The next question, essentially, previously I told you that it is not, it is completely balanced. Whatever supply you have, everything is equal to demand. Here you have 2200 as supply, 8800, 900, 1700 plus 500, 2200 as demand. So both are equal. So that is called a balanced problem. But you can have scenarios where the total demand is not equal to supply. Then the model is unbalanced. Then what we do, we add a slack variable, or instead of a slack variable, what we say, what this question is asking is, we can always add a dummy source and a dummy destination to restore the balance. Is that true or false? So what we mean is, let's say you have the same diagram we have. We have a source of say 900 here and say 600 here. They're going through some network, which we, let's say I am not drawing anything, but then I have different destinations. Let's say the first destination gives 100, the second destination gives 200, the third destination gives 300. Now here supply is not equal to demand, right? So now what can I do? Supply is not equal to demand, but whatever we have written the equation, whenever we have written all the equations, we have assumed flow conservation should be valid, which means supply should be equal to demand. Otherwise, our equations are wrong. Our model, our assumptions are wrong. Our model is not correct. So to make that correct, what he's saying is we will add some dummy source or dummy sink. So what he's suggesting is, what this question says is, we'll add a new source or new sink, whatever it is. So for example, you can do it in two ways. Now you have 900 plus 600, 1500. Here you have 600. To match that extra 900, you can keep it. You can keep a dummy sink like this. So this is my dummy sink. This is not existing in reality, but once I keep that, then everything will be balanced, right? So I can solve my equations correctly. So what this question says is, you need to add both a dummy source and a dummy sink, dummy destination. Do we need both, or one is sufficient? If it is like, if the supply is greater than demand, then what you have to do is add a dummy destination. Yes, if it is less than that, then you have to dummy source. So one is sufficient. You don't need both. So this is false. So instead of and, if it is or, then it would be correct. Okay. This is another problem. Instead of the cost, these are the probability values. So you can think of this like, you want to move from place 1 to place 7. These are the different roads that you can take. And the number here tells you the probability that you will be, let's say, the traffic is too high, or maybe the police will stop you on that particular road if you take. So if you want to move from point 1 to point 2, then there is a 20% chance that you will be stopped on that particular road. If you want to move from point 1 to point 3, then there is a 90% chance that you get stuck on that road. So you'll eventually have to choose a route where this is essentially, these probabilities will actually be like costs. So you want to take the roads where where the probability of getting stopped is less. That is essentially saying your cost will be less. But then this problem is different from the cost problem in a different way, because how do you, if you want to move from point 1 to point 4, let's say want to move from point 1 to point 4, what is the total probability that you will get stopped? Yes, I want to go through this part. I want to go to from 1 to 2 and from 2 to 4 I want to go. Then what is the probability that I'll be stopped? How do I do that? So it has two things. First, I have to take 1 to 2. So what are the different scenarios that you have? In order to be stopped on path 1 to 4, you have to go from path 1 to 2 and be stopped there. Like you can be stopped either in this place, or you can be stopped in this route. So if you are stopped in the first route, it will be point 2, or if you're point 2, or you can get stopped in the second route with point 8, or you can get it also means the other way. Now let's say if you are not stopped in the first route, doesn't go like this. So first thing is you get stopped in the first route, which is point 2. If you want to get to this path, it means that you should not get stopped in path 1 to 2. So there is, that is 80% chance you should pass through the first route, and then you get stopped in the second route. That is point 8, right? This is how you calculate the probability, right? Okay, let me put it in simple way. So let's say you want to move from 1 to 2. So P is P1 to 2 is this probability to be stopped on 1 to 2. Now what I'm asking is, what is the probability to be stopped on the path 1 to 4? Is equivalent to saying probability of not being stopped on 1 to 4, right? Let's say it is P prime. What is the probability of not being stopped on 1 to 4? I should not be stopped on 1. I should not be stopped on 1 to 2, or I should not be stopped on 2 to 4, right? So which means this will be equal to probability of not being stopped on 1 to 2 multiplied with, both should happen. So it should be multiplication, right? 2 to 4. I should not be stopped on 1 to 2. I should not be stopped on 2 to 4. What is P prime 1 to 2? Is 1 minus 0.2. And this is 1 minus 0.8. So P1 to 4 will be 1 minus 0.8 times 0.2, some value. So that is the probability of being stopped on the path 1 to 4. So like that, I need to choose the path from 1 to 7, which will give me the least probability of not being stopped. The difference between the previous and this problem is now you are having multiplications here. So previously we are just having additions, right? So it is whenever we want to calculate the objective function, all we are doing is sigma, like this multiply with. So it's the same problem. You again, your variables will be the same. Xij, Xij will be either 1 or 0. 1 if you take the root, or you not take the root. This will remain the same, but my objective is where the problem comes. I cannot write my objective function as 0.2 times x12 plus 0.8 times x14. I can't do that, right? Because that has no physical. So what should I do now? We just use a trick here. So what we do now is, okay, instead of trying to minimize the probability of being stopped, we'll change the problem to maximize the problem of not being stopped. That is the first thing. So this thing will change it to maximize not being stopped. Then that is essentially converting into some dual problem kind of thing. And the next thing that we do is, once we convert it into maximize not being stopped, what is the probability of not being stopped? It is just the multiplication, right? Now what we do, if you apply logarithm here, will become addition. So the multiplication has now become addition. So this is where we initially, when we discussed some transformations on optimization problem. So our original problem might not be directly, you cannot solve them directly with whatever ways we have, but once we transform it, the transformed problem can be easy to solve. Once you transform like this, so what you have to do is first convert this into a maximization problem. Second, all these weights, you take logarithm of them. Sorry. So if the particular weight is Cij, how we are transforming it is we are taking a logarithm of 1 minus Cij, right? This will be my new Cij prime. Now with this Cij prime, I can directly write my cost function as total cost as sigma Cij prime times Xij. If I take that root, that will be included into 1. If I do not take that root, that will not be included. So that will again be a linear problem that I can solve. Once I solve the entire problem, I'll get Xij, so that will give me the most variable path. Or essentially that is equivalent to saying the path that will minimize the chances of being stopped. Clear? Writing equations is same as what we have done before, just like this. You write down x11, x1, x12, x13, all this thing, and then you write this objective function, and then you write all the constraints. At every point, you write the same constraint, incoming equal to outgoing, except the source and destination nodes. Then you write down the matrices like this. Then you will get. So I don't think I have to do that here, right? That part is clear. Yeah. The only thing, the main point that here is originally it is not directly convertible into a linear thing. So all you have to think is first, how do I convert it? How do I transform it? First, the minimizing to maximization is a transformation that can always be done. Second, product cannot be directly taken care. So applied a log transformation so that it can be converted into a summation so that it will become a linear problem in the log space. Yeah. Okay. So this is some problem that I kept for Farkas lemma. So if you see that I have certain A, I have certain B, and I'm asking you to find this whether AX this particular solution exists or not. So if I solve it directly, if I just substitute it directly, what will it be? 1 minus 1 0 0. This is A. I'll take x1 and x2 equals to B. If I solve them, that will be x1 minus x2 equal to minus 1. The second equation also will give me the same thing. And I have the extra constraint x1 and x2 should be greater than. Can I find a solution for this? I can always find a solution like this, right? Say take x1 equal to 1 and x2 equals to 2, then that is a solution. Sorry, I didn't get it. This is it's 2 by 4. Oh, okay. Sorry. Okay. Anyway, that will be going to 0. So I have x1 minus x2 equals to minus 1. It's the only equation that I will be getting, subjected to the constant x1, x2, x3, x4 are greater than equal to 0. So can I get a solution? I can always take x1 equal to 2 or say x1 equal to 1, x2 equals to say 2, and remaining x3, x4 equal to 0. That is a solution for this problem. I can have infinite solutions, but let's say I don't want to solve this. Without even solving this, can I say the solution exists or not? Yeah, so how do I do this? So what do we have in the Farkas lemma that we can use it here? So what do we have in the Farkas lemma? We have AX, just copy paste. Oh, okay, I can't copy paste that one. Okay. So which of these is true? So we have A transpose Y equal to minus B and Y greater than equal to 0. This is the condition that is given there, right? So A transpose. So this is my A transpose thing, and this is here what we are trying to equal to minus C and Y greater than equal to 0. If there exists a Y for this, then Farkas lemma says there exists an Then the other statement will be false such that Ax less than or equal to 0 and C transpose X less than 0. If this is true, the other one will not be true. So what we are trying to do now is we do not know whether this is true or false. Let's say we do not know true or false. So we directly go to the next statement. So what does the next statement says? We try to see what is Ax. What is Ax? So that will be 1 minus, 1 0 minus 1 0 0 1 0 minus 1, because I have to take a transpose of this here, right? And that is why. So now it will be, so I have two constraints, so it will be x1 and x2 less than or equal to 0, right? Now what is C here? C is essentially minus of whatever I have there. So that will be C transpose. I'll just write the C transpose directly. 1 1 into whatever x I have is less than 0. So what we need to check now, can an x exist for this particular case? If an x exists in this particular space, then y will not exist. If x does not exist in this particular space, then y will exist, right? That's what Farkas lemma says. What does this statement mean? What does these conditions mean? Now the problem became a 2D problem. So originally it is a 4-dimensional problem, but now once we converted it, now it's a 2D problem. So I can just visualize this. What are these constraints? Each of these constraints. The first one is x1 less than or equal to, x1 is negative, right? X1 negative, x2 negative, all of them are negative. So this is essentially my third quadrant. That's what it shows. Now this is my third quadrant. And what is my objective function? X1 plus x2 being negative. So this is my x1 plus x2. And that is negative. So this, and I can keep going negative. So what happens for this if I keep going like this? And then you will end up having nothing. So the only solution that you can have for this is when you reach here, only with the origin, which we are excluding by saying that it is strictly less than 0. Yeah, so it would mean that you cannot find an x such that it satisfies both of these together. Oh, sorry, I think I've drawn this incorrectly. 1 second. You just take the 2D. You have to just look at the constraints properly. So the first constraint is x1 less than or equal to 0. The second constraint is minus x1 less than or equal to 0. This would give me x1 greater than or equal to 0. So I have to satisfy both x1 less than or equal to 0 and x1 greater than or equal to 0. So only origin will be the solution. And similarly, x2 less than or equal to 0 and minus x2 less than or equal to 0. So that should imply x1 equal to 0. And this would imply x2 equal to 0. If both x1 and x2 are 0, then I cannot draw any line. That line has to pass through origin. That's the only possibility, right? If both of them are 0, it has to pass through, it will be only this point, no other point. But we strictly said that it should be less than 0. So x is not existing. So if x is not existing, then y should exist for sure. You don't even have to solve anything. Without even solving, we can say that y will exist, solution will exist for this problem. Okay. This is some simple problem, just to kind of highlight it. So this is in the, let's say this is a primal problem. How do I convert it into dual? So first start with this one. Maximum becomes minimum. Now convert the variables and constraints thing. So what are the variables here? X1 and x2 and x3. They become the constraints, right? So the constraints will be, or even before that, let me put one more thing. In our standard form, what is the form that we have? Everything are equalities, right? In the primal form. If you convert the above equation into primal form, how would it be? Yeah, minimize minus 5x1 minus 12x2 minus 4x3 subject to x1 plus 2x2 plus x3 plus some slack variable less than or sorry. After adding the slack variable, this will be equality constraint. and then you have 2x1 minus x2 equal to 8, and then you have x1, x2, x3, and s greater than or equal to 0. Now this is in the standard primal form. So you are trying to minimize C transpose x subject to Ax equal to b and x greater than or equal to 0. Now if you convert into dual, what is the dual form of this? Maximize. What is the dual form? This is my primal. What is my dual? Yeah, maximize. What will come here? Your whatever is your right hand side of this, that will go with the previous one. That will be your objective p transpose. You will have some new variable y. What will be the constraints? A transpose y less than or equal to c, right? So now seeing this equation, this is the primal form. How will the dual form look for this? This minimization becomes maximization. So what is my b variables here? So I have 4 variables here. This is 4 variables, 2 constraints. So how many variables will I have here? Here I will have 2 variables and 4 constraints. So what will my variables are y1 and y2. So what will be the values? What are the constants that I have to multiply here? Sorry, this is greater than or equal to c. So what will it become? If you see, so what is the y1? So what is this b here? This b is prime from the primal is going into the objective here, right? What is the b here? This one, 10. 10 and 8. These are the b values, right? If you convert this into matrix form. So these will come into my dual space. So 10 into y1 plus 8 into y2. That will be my objective function. Now what will be my constraints? If you see, it will be A transpose y greater than or equal to c. So again, it will have the variables y1 and y2. But how many variables will I have? So I have 4. So previously there are 4 variables. Now I'll have 4 constraints. So it will be something like 4 equations will be there now. And each one of them will be some inequalities. And the inequality, this c is coming in the inequality. And that c should come from here. So what we have here is greater than or equal. Is this greater than or less than or equal to? Can you check this one? Just a second. Yeah, it becomes less than or equal to. Since because of the minus, it will become greater than or equal to. Yeah. So what is the c here? C is the coefficient of x, right? C transpose x. C is the coefficient of x. What is the coefficient of x1? Minus 5 here. That comes as c here. What is the coefficient of x2? Minus 12. That comes as here. X3. And the last variable is s. S coefficient is 0 here, right? So I can write this as plus 0 into s. Okay. Now what are the coefficients here? This is basically A transpose, right? Here the coefficients are A. The coefficients of I are A transpose. So all you have to do is transpose this coefficients here. This is one, the x1 coefficient, this one will come here. This 2 will come here because I'm doing a transpose. Similarly, the next coefficient will come. Next coefficient is 2y1 minus y2. The next coefficient is y1 plus 3y2, and the last coefficient is y1 plus 0y2 greater than or equal to 0. So why are these greater than? These are less than, right? A transpose y less than or equal to C. Okay. So this is from primal to dual. Now you can always do another stuff here. So if you see there, all these coefficients are negative, right? So I can make all of them positive. How do I make all of them positive? I just multiply with minus sign. If I multiply this entire equation with a negative sign, then this will become positive. So can I write the above? This is also equivalent to another transformation. I can write something like this: 10 times z1 plus 8 times z2, such that z1 plus 2z2 is less than or equal to 5. 2z1 minus z2 is less than or equal to 12. z1 plus 3z2 less than or equal to 4. And z1, sorry, if I multiply with the minus sign, the inequality also changes. Greater than or equal to 0, where z1 equal to minus y1 and z2 equal to minus y2. Can I do this transformation from here to here? So all I'm doing is multiply with minus sign on both sides. So this will be minus y1 plus 2 into minus y2. Minus y1 I'm writing as z1. Minus y2 I'm writing it as z2. This minus goes off, but because I multiply with minus, the sign also changes. Okay. Then the objective also, because instead of putting minus, so I just changed maximization to minimization, because maximizing a negative quantity is minimizing the same multiplied with minus 1, right? Okay. So this is a dual problem. So from this maximization, you eventually came to the dual problem, something like this, with just 2 variables from 4 variables. Yes. Which one? This one. This is basically, if you see, this is AX, right? So here, if you see the A matrix is something like 1, 2, 1, 1, 2, minus 1, 3, 0. This is A matrix. So what we are doing is A transpose Y. So what is A transpose? 1, 2, 2 minus 1, 1, 3, 1, 0. I've just multiplied that with X by 1 by 2. Okay. Okay. This is again the last problem is an formulation problem. So we have certain distances, certain cost. You need to minimize the total transportation cost. This is also the same one that we have. So here we have 3 sources and 2 sinks from S1 to T1 and S1 to T2. Similarly, S2 to T1, S2 to T2, S3 to T1. But I think by now it is clear for you. So what am I trying to do? I'm trying to minimize the total cost. So my objective will be each of these links has, say, 1, 2, the first number them, and my decision variables are whether I take that particular route or not. So xij will be 1 if I take that route, 0 otherwise. Now Cij is already given here. So the cost will be, so the variables will be, what are the variables? x14, x15, x24, x25, x34 and x35. These are the variables. What is the cost? The objective function is minimizing the cost. So it will be minimized x1 to 4, whatever is the cost. 1 to 4, the cost is 80 times that particular distance. So I didn't put it in appropriate unit. So this cost is essentially the cost per unit distance that you travel along that particular route. So the total cost you will get by multiplying this and this. Yeah. So you get the cost like that, and then you put them here. So that will be C124 times X14 plus C125 times X15 and so on. Constraints are the same. At each and every node, this is a source node. So incoming will be 0. Whatever is outgoing should be equal to -1. And similarly, this is my target node, destination node. So whatever incoming minus outgoing is 0 equal to 1. You don't have any intermediate nodes here. Yeah, so I don't think I don't think I have to write the equations again. We are already out of time. Yeah, so this is clear. So basically what we discussed in this week is mostly on how to formulate optimization problems, especially for this max flow, or we didn't explicitly solve min-cut problems, but the shortest path problem we have solved. And then we discussed Farkas lemma and the complementary slackness condition. Maybe on this I'll bring up more problems in the next week. Once we discuss tangent function stuff, then it will be much better to have good examples on that. Yeah, these are the questions I have for this week. Yeah, you have any other things that you want to discuss, or we can end the session? Thank you.